Am I audible?
Yes, sir, you are audible.
Rana sir?
अब बोलो
Audible? Rana साहब?
हाँ हाँ हेलो
Yeah. You are not audible, sir.
Hello.
Yes, sir, yes.
Good morning to one and all.
Sir, am I audible to you?
Yeah. Now you are audible.
Okay, sir. तो start करें हम.
Yeah, we can start.
Rana sir, am I audible?
Yeah, you are audible.
तो करें हम process start करें.
Yeah, please go on.
Okay, candidates. So our next speaker is Dr. Ashwani Rana, and giving the brief of Dr. Ashwani Rana. So Dr. Ashwani Rana has received his BTech degree in Electronics and Communication Engineering from NIT Hamirpur, and then MTech in VLSI Technology from IIT Roorkee, and he did his PhD degree from NIT Hamirpur. And so presently he is with the department associate professor, and his research interest include modeling of semiconductor devices, then low power high performance VLSI circuit design, and emerging integrated technologies. And he has are ongoing in his area, and he's having and guided more than 50 MTech student and then PhD also. And he is the member of the ISTE, and present invite Professor Ashwani Rana to deliver his talk. Sir.
Yeah. So, am I audible? Yes, please. Hello, Ashish, am I audible?
Yes, sir. Yes, sir. Yes. Audible.
Okay. So I would like to present some recent trends in VLSI technology, which will include the material and the device aspect. So this is the outline. So material aspect of VLSI technology, and then the choice of technology for VLSI arena, and the Mosfet basics, and the scaling principle, and then the nanoscale effects in Mosfets. So I assume that everyone is well versed, at least with some semiconductors, right? So as far as the benefits of VLSI is concerned, so it reduces the manufacturing cost, and cost matters a lot in any commercial product. So it improves the designs, maybe speed, maybe in terms of the power, and then lower parasitic capacitance, parasitics. So because of lower parasitics, we are able to obtain a devices of higher speed, so that we can handle a high frequency signals also, and lower power consumptions, because devices are of small size. Therefore, roughly the power is directly proportional to area of that particular device. So therefore, we are getting a lower power devices, and obviously they are physically smaller because of the progress in VLSI technology. So as far as the material of choice for the VLSI technologies are basically a germanium, silicon, and gallium arsenide. So I would like to discuss their merits, and but converse on a material which is of use nowadays. Okay, so if you see a band gap, then band gap for germanium is 0.78 electron volt, and then for silicon it is 1.21 electron volt, and then for gallium arsenide is 1.2 electron volt. And there are two values mentioned in this band gap column, R in row. So the upper one is at absolute zero Kelvin, and the lower one is at room temperature, right? Okay, so these are the two different values. Now the next question comes that what is the importance of band gap? Why do we study the band gap? Okay, so if you see, the band gap is a gap, energy gap, or between your conduction band and valence band. Okay, so what does it mean that in case of, for example, if I compare two material over here, for example, germanium, not a germanium, but a silicon and gallium arsenide. Okay, so if we see silicon, that is maybe 1.1 electron volt and then 1.4243 electron volt, it means that for making the conduction in silicon, a 1.1 electron volt energy must be given from outside to the semiconductor, so that it can miss, so that the electron can move to a conduction band, and in conduction band we have a lot of empty space, and in that empty space, the electron can move from one position to the another positions, right? So movement of electron from one position to another position in a given time is basically a current, right? So it means that I have to supply a 1.1 electron volt energy from outside, right? So in electronic term, if we see, we can say that we have to supply a energy in the form of a vice, right? Voltage. So it means that electron, which is maybe we may consider germanium, okay? Electron in germanium require energy 0.67 at room temperature to jump from conduction band, valence band to conduction band, right? And this is the beauty associated with the semiconductor, because the semiconductor will not jump or semiconductor will not conduct unless until we supply some external force, right? External energy. But because of the rise in temperature, that is because of in room temperature, the sum of the electron may acquire some energy which is equal to half kT, right? And because of that energy, they may jump from valence band to conduction band, even when we have not applied some external force. So it means that the electron can jump from conduction valence band to conduction band more easily in germanium as compared to gallium arsenide, right? And this energy, that is 0.6 electron volt energy, may be acquired by the electron because of their thermal energy, right? Half kT, and they may jump from valence band to the conduction band of their own. That is without applying some external energy. So this unwanted movement, that is from conduction band, from valence band to conduction band, is basically unwanted movement, and this unwanted movement basically will give rise to some current, right? So that current is also unwanted. So we call that current, unwanted current, in electronic term as the leakage current. So there are chances of the leakage current, more chances of the leakage current in the germanium as compared to the gallium arsenide, because in gallium arsenide the barrier through which the electron has to jump is large, that is 1.43 electron volt. Okay, therefore if we consider the physically significance of this material, it clearly states that the material which is having a lowest band gap is more prone to leakage current as compared to a material whose band gap is large. Okay, therefore if we compare all these three material, we would arrive at a conclusion that gallium arsenide is the better material because it will give rise to a low leakage current. Okay, therefore whenever you will go to the market and your team leader in your technical team will ask you that go to a market and bring a material which is of low leakage in nature, what would be your answer while you will visit a market, right? So you can ask your vendor, salesman market that kindly give me a material of this much band gap. Okay, so this is the physical significance of the band gap in materials, right? So then we can say mobility. Second property of importance is immobility, right? And this band gap is related with the power consumption also, right? Because if the leakage is more, so it will consume more power, right? So you can say that the devices which are made of low band gap materials are more power hungry. So they will consume more battery, and battery has some money involved in it, right? So second property is basically the mobility, and in the mobility you can see that mu(n) means mobility of electron, mu(p) means mobility of hole. So the mobility values are written for all these three different materials, and you know that mobility is directly proportional to the drift velocity, right? So BD, that drift velocity is equal to mu into E, right? So we can say that mobility is directly proportional to the drift velocity, and velocity is proportional to, or you can say velocity is equal to x by t, distance by t. Okay, here distance is between source and drain. If I consider a Mosfet as a device, then here distance is between source and drain, that is length of the channel is, you may take it as x. Okay, then the electron has to cover that distance x while moving from source to drain, maybe in a given time t. So it is x by t. Okay, so you can say that this time is also important, and distance x, which is between source and drain, it is a fixed parameter. And now you can say that this mobility is basically a q tau by m, right? Okay, so this determines the value. And in case of mobility, we would like to find out the time taken by electron while it is moving from source to drain. Okay, so T is equal to, you can say, x by v. Okay, x by vd, and also it is proportional to equal to x by mu. Okay, so ultimately you can say that your time is inversely proportional to mobility. So from here you can determine the time which is taken by electron. So if you see the mobility values, for example, you concentrate on a mobility of electron in all these three materials are lowest and highest. So lowest mobility is in silicon and highest is in gallium arsenide, right? So if the mobility is highest, then it is inversely proportional to time. Therefore, the time taken by electron in gallium arsenide will be the smallest as compared to the your silicon. If time is smallest, then time is inversely proportional to frequency also, right? Okay, if time is smallest, frequency is high. It means that gallium arsenide or the devices, maybe Mosfet, maybe BJT, maybe a diode, right? Made of gallium arsenide will be faster in nature. Okay, and it is faster in nature means because it takes a small time to move from your source to drain, then the frequency which is handled by the material will also be high for a gallium arsenide. It means that the MOSFET, which is made of gallium arsenide, can handle a more frequency or can handle a signal of high frequency as compared to the your silicon. So therefore, in terms of mobility, if we have to choose a material for a MOSFET for a device, then it is a gallium arsenide. Resistivity, the second, not second but third. Yes, am I audible? Yes, please. Am I audible?
Yes, sir, you are audible.
Okay. Then third property of this material is resistivity, right? So you can see these values. It is a 47 ohm centimeter and it is 2.3, not 23, but it is 2.3 into 10 power 5, and then it is order of 10 to the power 8, T8. Okay, for gallium arsenide. Resistivity is basically related with the breakdown strength of a material, right? If material have a high value of resistivity, its breakdown strength will be more. So roughly I can say breakdown strength is the strength of a material before it is break down and can do its functionality well. Okay, so if these three values are observed or noted, you can see that gallium arsenide has a high value of resistivity and has high breakdown strength. And if it is a high breakdown strength, then what is the physical significance of it? Okay, suppose we are dealing with electronic circuits, and also we are dealing with electrical circuits, right? So in electrical circuit, we also used to use the devices, electronic devices, right? So in electronics, we use a battery of the maximum battery of 5 volt, right? Where nowadays we use the battery of the order of 1 volt. But in electrical circuits, we use a voltage of high value, right? Maybe 33 kV voltage, maybe 11 kV voltage, right? Like that. So high voltage. So means we should have a material which can tolerate that high voltage, right? We should have a material which has a high breakdown strength so that it can function without breaking down at that high voltage. So therefore, if we want to use a material for your high power or low, high power and low, not low, but high power and high voltage applications, we have to go with the gallium arsenide material, or we have to go with a device which is made of gallium arsenide. As far as manufacturability is concerned, okay, so it is not easy for germanium and it is easy for silicon, and it is not so easy for gallium arsenide also. Only because of the one reason, because the silicon technology has been matured in our system, and therefore if we process a material which is made of germanium or made of gallium arsenide, we have to go for a change, right? We have to change the technology, therefore its manufacturability is not so easy, right? And the most important parameter is also one is cost, right? So without a cost, for example, if you are making a mobile in India and making a mobile in China, then the mobile made in China will be cheaper one, more cheaper one as compared to the mobile made in India having the same features, right? Okay, so therefore people used to buy a mobile which is made in China, which is or you can say which is the cheaper one. Okay, therefore if we see, then the device made with germanium is costly, device made with gallium arsenide is also costly, and the device made with the silicon is the cheaper one, because your silicon is available in abundance in our country and also in other countries also, right? Therefore here if we see, it is the silicon which is favoring us to be used in technology. As far as application is concerned, germanium and silicon can be used in all the application except in optical application, whereas gallium arsenide can be used in all the application, even including the optical applications, right? Therefore, gallium arsenide in that sense is a more usable material to be used in the technology, right? Now if we see all these properties, then it appears from the remark column that gallium arsenide is most suitable material which can be used in your IC technologies, right, in integrated circuits, as compared to the germanium and silicon. So germanium is outrightly rejected because of its small band gap, because it is more leaky one. Okay. This leakage power has importance. For example, you have a mobile and you have switched off your mobile for some maybe for a reason to be used later on for an important application. Then you can see that after 3 days, if you open you switch on your mobile, you will find that your battery might have been drained out, right? So this is because even when you are not taking any job or any work or any function from the devices, the devices used to consume a power only because of the low band gap property, right? So therefore, if we have a your germanium, we have a mobile which uses devices made of germanium, they will be drained out immediately, right? As compared to the gallium arsenides. Okay, so therefore, we should use a gallium arsenide in our technology. But we are not using the gallium arsenide in our technology. Instead, we are using a silicon as a technology, as a material of the technology, even as on date. Okay, so because gallium arsenide is a compound material, right? It is a bivalent, you can say, compound material. So here the processing of gallium arsenide while making devices in integrated circuits is difficult, because gallium and arsenide has a different melting points. So most of the techniques which are used for the fabrication of ICs are basically high temperature techniques, right? So at that high temperature, the gallium and arsenide both having a different melting point, so they melt at different temperatures, thereby disturbing the stoichiometric configuration of the compound, that is gallium arsenide, right? So gallium arsenide means 50% gallium and 50% arsenide, right? But while we are using it in a high temperature processes technique, the one melts ahead of the other, and thereby disturbing the, you can say, the stoichiometry of the compound. Okay? Therefore, ultimately, we use a silicon as the technology, right? So, by studying these properties, or by discussing these properties, I could conclude that the Willisite Technologies, as on date, uses the silicons because of some practical difficulty with the gallium arsenide, right? Or even if we use a gallium arsenide, then the ICs which will be made with the gallium arsenide material will be of high cost, right? So which we cannot tolerate at present. Okay. However, we use some application specific ICs with gallium arsenide also, right? So those ICs which can handle a high frequency signal, which have to handle a high frequency signal, in that case we use a gallium arsenide ICs also, right? But we have to bear the cost. Okay, and then I would like to discuss the choice of technology, right? Which technology we could prefer in VLSI as on date, right? So we have two technology, that is VJT and the Mosfet. So VJT is the older one, and the Mosfet is taking up. Even the Mosfet may die within few years, or maybe in a decade. Okay, because of its high leakage associated with it, right? Or even we can mix both the technology, that is VJT and Mosfet, by taking advantage of the each technology, right? So if we have to compare these BJT and Mosfet technology, we can compare these technology in terms of their structure, size, driving capability, speed, power dissipation, gain, and also the fault during the manufacturing. Okay, so structure, if you see, the structure is simple with the Mosfet as compared to the BJT. Size is a major bottleneck in the use of BJT. Otherwise, the driving capability, you can say gain and speed is favoring the BJT, right? Okay, but the size is not favoring the BJT, and because of this limitation, that is because of the size and power dissipation properties, the feature of your MOSFET, we have replaced the BJT with the MOSFET, right? So size, you can say that roughly, you might be knowing that one BJT, the size taken by one BJT of in the IC, or you can say the silicon area taken by BJT in an IC is equivalent to the silicon area taken by 15 number of the MOSFET. Okay, roughly 15 number of MOSFET. So one BJT cannot do anything, but 15 number of the BJT, maybe they may design your NAND gate, they may design your inverter, even a half adder. Okay, so you can see this size difference. Therefore, because of this size difference, or because of the small size of the MOSFET, now we are observing that we have an electronic gadget which we can carry in our pockets, right? Okay, which is not possible in earlier days. Okay, therefore, because of this size property, we have replaced the BJT with MOSFET. Driving capability is also high with BJT, not with MOSFET. Speed is also high with BJT, not with MOSFET. Power dissipation, so roughly the power dissipation is directly proportional to the size of that particular device. So you can see the size of a MOSFET is very small as compared to your BJT. Therefore, this property is also favoring your MOSFET, right? Okay, so MOSFET consumes very less power. Gain is related with the driving capability. If you have a high driving capability, you will have a high gain. So gain is also favoring a BJT. Fault tolerance, but fault tolerance is favoring the MOSFET because the manufacturing process is very easy for MOSFET. Therefore, it is less prone to the defaults. So you can say that the default, power dissipation, and size and structure, these are the features which are favoring the MOSFET as compared to the BJT. Therefore, MOSFET technology is more superior to BJT. Okay, so technology ultimately focused is on, if we see the material and technology, so it is a silicon based MOSFET. So you can say the old wine in new bottles. So why I have written is this, that because the worth of a BJT and MOSFET almost took place in the same arena, that is somewhere around in 1960, but BJT matured ahead of the MOSFET because MOSFET is suffering from one problem, that is the oxide and your channel interface, right? So in channel you have a silicon and oxide, you have silicon dioxide. So the interface between these two is not good. So these interface has given some defects, and because of that defects, it causes the leakage. But nowadays we have good technologies which can give a good interface, and hence we are using the MOSFET since 1980. Okay. So this is the MOSFET structure. Okay. You might be knowing N plus is maybe N plus source and maybe N plus as drain, oxide and metal. Okay. And then P is a substrate. It is made of silicon if it is a silicon and MOSFET. this Venn diagram. Okay, here concentrate over it, right? So I think we can leave this because everyone knows MOSFET. Do you have the knowledge of this structure of a MOSFET? Yes, please. Yes, please. Can I skip this or not? Yes.
Yes, sir.
Can I skip?
Yes, sir.
Okay. So here we can quickly go through this region of operation in inversion mode, right? So you can see that when your voltage at gate is greater than VTH value, right? So it gives rise to a linear mode, and as your the VDS, that is the reverse bias applied to the drain, should be less than VGS minus VT. Okay, so you can see that this blue portion indicates basically the channel region, right? And some of the researchers have derived this current in the linear region. So this is beta. Beta is basically mu n Cux by 2, not 2, mu n Cux W by L, right? So within the bracket is VGS minus VT, and then VDS minus VDS square by 2, right? So if you plot this expression, this expression is basically expression of a parabola, right? So you see on the right hand side, so it behaves like a parabola, right? Okay, but the expression of a current, or you can say the current values are not like this as far as the practical aspect is concerned. If you plot this curve practically, you will find a different curve. It will not be a parabola, right? But up to the value VGS minus VTH, which you can call a pinch off value, the both curve will match. After this, the parabola will decrease to 0, but in actual practice, the current will not decrease to 0, right? So we can say that this equation is valid up to VGS minus VTH, right? So for a VDS value less than VGS minus VTH value, and this behavior is known as a linear because here current and voltage are almost linear. They are not exactly linear, but they are almost linear. Therefore, it is known as a linear rhythm, right? So pinch off, that is the edge of saturation, right? So this P point, so this P point indicates the pinch off, which is onset of saturation, right? So at this point, you can see if you see the channel is just touching the drain, okay? So it's just touching the drain, so channel is reduced to inversion, to zero inversion charge at the drain, okay? So drifting of electron through the depletion region between the channel and the drain. Why this is happening? Because as we are increasing the drain voltage, VDS voltage, the depletion layer across the drain increases, so therefore the channel takes this type of shape, okay? So here you can see that after this the current will be almost constant, right? So you can see over here saturation mode, and this your VDS is greater than your VGS minus VTH, right? Or VTO here. So here what happens that when electrons will move from source to drain, they will move through your channel, right? But now channel is shifted away from drain. Yes, can anyone can tell us why the current will flow even there is no channel? The current or the electron will move from source to drain only when there is a medium of conduction, that is the channel. But now channel has been shifted, and this yellow region between the edge of a channel and drain is basically the inversion layer, that is the kind of a insulator. Yes, why this even why there is a current even after this structure? Yes, anyone can have an idea? Yes, please. How the electrons are traveling from the edge of a channel to drain, although there is no path. How they are traveling? Yes, please, anyone? Yes? No? No answer? So we are applying a drain voltage between drain and source, right? So source terminal is the same as the as the edge of a channel region, right? Therefore, whole of the drain voltage is dropping across this yellow region. That is the point of channel and the your drain, right? So therefore, in this channel, there is a huge drop of the voltage, you can say, and the electric field which is present in this region, you can say that it is the VDS by this region. You can say that the length of this region, that is delta x, you can say. Okay. So what will happen? So the electric field is your VDS by and delta x, and this delta x is very small. Therefore, the electric field which is present in this region is very high, and this electric field sweeps the electron from the channel to the drain. Okay. So, but the area through which these electrons can be swept is basically very limited, right? Therefore, the number of electrons which are being swept from the edge of the channel toward the drain remain almost same. Therefore, after pinch off, the current almost remain constant. Okay, and while substituting this VDS equal to VGS minus VTH, that equation reduces to IDS equal to beta by 2. Beta is mu n Cux W by L. Okay, VGS minus VT square, right? So this is also this is following a square law, right? So this square law means it will saturate at some point, right? Therefore, this equation holds good in saturation region, right? Therefore, if we see the model, this model equation, level 0 model, or this is Suchman-Hodge model, not his but Hodge. Suchman-Hodge model, and this is also known as the level 0 model. So we have two mathematical models, modeling equations. So first upper one is valid for linear region and the lower one is valid for saturation region, right? So this model gives accurate result for long channel MOSFETs, and when the channel length of the MOSFET is greater than 1 micrometer, that is the 1000 nanometer, but could not give accurate results for smaller geometry MOSFET, and because of the two major limitations. So this is the first correction to level 0. Non consideration of doping diffusion from source and drain into the channel. There is an additional, or you can say there is a doping of source and drain. Okay, because when the dopants are added concentration to the lower concentration, and they will move toward your channel side, right? So this you can say delta L and delta L on both sides. Therefore, the effective channel length after correction is L effective is equal to L minus 2 delta L, right? So this correction need to be incorporated. Okay. And second is this correction, right? The channel length modulation, because when we are increasing the VDS value greater than the VDS saturation. VDS saturation is VGS minus VTH value. Okay. When we increase this value, so the channel is shifting toward the source, and therefore there is a pinch off point is shifting toward the source, and then the length is also decreasing. The channel length is also decreasing. So it is decreasing by a length xd in a given figure. Okay. So this is the second correction. When we apply the both correction, okay, so it becomes a level 1 model equations, and your because this happens only in the case of your saturation region, nothing is happening in the linear regions. Therefore, linear region equation will remain same, but in your saturation region, the equation changes to beta by 2 VGS minus VT square. So one additional term came into this equation, that is 1 plus lambda VDS. So these two equation becomes when these two corrections are added, so model equation changes, and then we call it as a model 1. Similarly, there is a limitation on model 1, that is we have not considered the substrate wise, okay, then we have not considered the effective mobility. Okay, so because of the collision of the charge carrier in a channel, and the mobility basically decreases, right? Effective mobility decreases. So these two corrections, you can say, has not been taken into care in level 1 model equations. Therefore, when these are taken into care of, your level 1 equation changes to level 2 equations, right? So therefore now you can see that equation level 2 models. So linear region remains same, but you can see the saturation region model equations, they have changed drastically, right? So level 1 and level 2 models are accurate enough for long channel devices, right? But for short channel devices, we cannot use these equations. So therefore limitation of level 2 models are the short channel effects. Okay. As far as the other spice models are concerned, so we have a advanced models, also the C models, right? So as the level of model increases, it becomes more abstract and empirical in nature. Empirical in nature means we are not then driving the equations, but we are using the empirical parameters, and empirical parameters are nothing but they are the fitting parameter. It is a kind of hit and try, right? Therefore you can see that the same models version 4.5 has 103 fitting parameters, right? So because it becomes a cumbersome to drive the model equation then. So then in place of these driving a model equation, we used to add the empirical parameters so that the result obtained from the model equations and from the practical device matches to great extent. Okay. This now how improvement in technology could be done exactly, right? So how to improve this performance, right? So the question, the answer is by scaling the miniaturization, that is scale the devices, that is the make the devices more smaller and smaller, and that we call it scaling down. Okay, so the scaling down is done by doubling the transistor density. So we have to, while we are moving from one technology to another technology, that is, for example, we have a 0.13 micrometer technology and we want to move from 0.13 micrometer technology to 0.09 micrometer technology, that is from 130 nanometer to 90 nanometer. We will only move when these three things will be achieved, right? What is the first one? The transistor density should be doubled. What is the second thing? That is the gate delay should be reduced by 30%, right? Or we can say that the frequency must be increased by 43%. And the third is the reduction of the power must be by 50%. Therefore, we are not reducing from 130 nanometer to a 110 nanometer, and not to a 100 nanometer, not to a 95 nanometer. We are reducing from 130 nanometer to a 90 nanometer because we are achieving these three objectives. Okay, and then from 90 nanometer to objective to 65 nanometer, then 65 to 45 nanometer, and so on. But we have to achieve these three objectives while moving from one technology node to another technology node. This is the scaling principle, right? This is the constant field scaling, that is the field should remain same whether the device is a long device or a short device, right? So the upper equation has been written for a long device. So that is del square phi by dx square is equal to minus rho by epsilon. This is Poisson equation, and is equal to minus q1 by epsilon. Okay, where phi is potential and is doping and x is the dimension. Okay, these are for large geometry. And then motivation for scaling. Why to reduce the scaling? What is the most motivation? That is, we should reduce the device dimension such that the field which is obtained by electron or field which is experienced by electron in a longer geometry and a small geometry should remain same. Okay, so this is the broader objective motivation, that is the field or the force which is experienced by an electron in a smaller geometry or in a larger geometry should remain same. That's why it is known as constant field scaling. So let's move toward a smaller geometry, and suppose the dimension potential is phi dash, doping is n dash, and dimension is x dash. So this is equal to lambda phi, lambda n, lambda x. Supposing that lambda is less than 1. Okay, so then we started with the smaller geometry and substituted the phi dash as lambda phi x by lambda x, and ultimately you will find that the equation, if n dash is equal to n by lambda, then equation 1 will become like something like this, right? Lambda is taken outside, so it is lambda, then lambda from lambda x square, so it is lambda square minus q n by lambda. If you equate this, lambda goes with lambda, then one lambda goes with another lambda on the right hand side. So this gives rise to the same equation. So if you see the first equation and last equation, both are same, right? So they are same if each potential is reduced by lambda, if each dimension is reduced by lambda, and each or doping is reduced by 1 by lambda, or you can say doping is increased. Okay, so then there is no problem in reducing the geometries. So this is a kind of a physically, you can see 0.8 micrometer. This is the figure of an inverter, right? So you can see this how the size is going to reduce. 0.8 micrometer to then 0.25 micrometer. You can see 0.13 micrometer. How the sizes are going to reduce. Okay. So ultimately scaling is done by reducing all dimension, by reducing all voltage, and by increasing the doping density. Okay. This is the, you can say that the status of foundries in our countries. Okay. So in India there is only one foundries, right? That is SL Mohali. In USA we have approximately 10, but in Taiwan there are 600 foundries. So you can see the on the left hand side figure is the Mosfet, which is fabricated in foundry. Okay, so you can see Taiwan is a very small country, but it has a 600 foundries, and Taiwan is earning its major GDP only through foundries, right? So change of technology is required in semiconductor. Therefore, India could not, you can say that tolerate that much cost while changing the technology from one technology node to another technology node. So, but while we are scaling down the devices, or while we are making the devices small, so there are some problems which are coming into picture. Tunnel current in gate oxide. So gate oxide is basically insulator, but when we are reducing the size or thickness of the gate oxide, so there is a flow of current because of the tunneling mechanism, and power dissipation is increasing, sub-threshold leakage is increasing, interconnect time, that is RC time constant, are increasing, then it also increases the power consumption. And because of the smaller dimension, there are some statistical fluctuations, right? Okay, so maybe a random dopant fluctuation, maybe another type of the fluctuations are there. Okay, so nowadays even the device is reaching its physical limit, right? So cause of scaling problem, why the scaling is not moving properly. So you can see that electric field tend to increase because of the supply, but supply voltage has not been scaled proportionally. We could not scale the supply voltage. However, we could scale other voltage which are applied to the devices, right? And another problem is that built-in potential, which is also voltage, is neither scalable nor negligible. We cannot neglect it at this small dimensions, although it is small value, but in small dimension we cannot neglect the built-in potential. Then the depth of source and drain junction cannot be reduced easily. They are also not scaled proportionally, I can say. And then the mobility decreases as the substrate doping increases, and when the doping increases, it gives rise to another type of the problem, for example random dopant fluctuations. Okay, sub-threshold slope, that's SS, is also not scalable. So because of these properties, there is a problem in the your scaling, right? So these nanoscale effects, that is source channel effects, what are these? So I'll discuss these quickly. So threshold voltage variations, right? Mobility degradation, velocity saturation, hot carrier, drain induced very lowering, drain source series resistance, punch through output impedance with Vds. Okay, so this is a threshold voltage variation. You can say that in the left figures, after 19 nanometer, the threshold voltage starts decreasing. So threshold voltage starts decreasing right? So it is good that threshold voltage should be of low value. Even the threshold voltage should be 0, so that when we excite the device, immediately the response is obtained. Otherwise, the response is obtained when the voltage across the gate reaches up to a threshold voltage, right? So therefore, this threshold voltage should basically, ideally it should be 0, but it is there, right? But when this scaling happens, threshold voltage starts reducing below 90 nanometer technology node. So reducing a threshold voltage, you can say basically it increases the leakage current, right? So you know that subthreshold current is exponentially proportional to your VDS minus VTH, right? So this as the threshold voltage reduces, leakage current increases, right? This is the mobility degradations. You can say mu naught is the mobility without a field, right? So when we apply a field, the collision happens, and because of the collisions, the charge carrier cannot move straight forward from source to drain. Therefore, they undergo they take some time to reach from source to drain. Thereby, ultimately, its effect is taken in mobility. So we can call it as a effective mobility. Okay. So it reduces the driving current, okay, and obviously driving current is IDS. So if it reduces the driving capabilities, so transconductance of the Mosfet will also be degraded, and hence the amplifier performance will also be degraded. So this is the velocity saturation, right? So velocity is equal to mu d is equal to mu n into E, right? So you can say velocity is directly proportional to the electric field until the electric field reaches a critical value EC, right? So for a value beyond this EC, the velocity saturates to its maximum value, and this maximum value is given by thermodynamics, and that maximum drift velocity is given by the thermodynamics, which is equal to under root 3 kT by Mn, where Mn is the mass of electron and star is effective mass of electron, right? So this is the saturation velocity, and this is the maximum velocity which we obtain, right? So this saturation velocity is modeled as Vd is equal to Vd max. You can say these are the modeling things. So we can skip this thing. We can also skip this thing, and here you can see the last equation, right? So here Id is equal to mu n Cux Wec Vg minus Vt minus 1 by 2 Vds. Here you can see that your current becomes directly proportional to your W, right? And there is a no L. That is, it is independent of the technology, and therefore ultimately you see this equation, and this equation shows that drain current becomes independent of channel length, and when device is under severe carrier velocity saturations. Okay. So again you see the another equations. ID, it becomes mu n Cx Wec Vgs minus Vt. Now this here drain current becomes directly proportional to Vgs minus Vt, right? So you can say this is kind of a linear equation. So this is just like a Ohm's law. So it means that nothing is being produced. Okay, under a sphere velocity saturation, I is equal to V square means we are enhancing the current. For example, I is equal to V square. So if I increasing the voltage by 2 times, current will increase by 4 times. So it means we are gaining something, right? So device is active. But here I is proportional to V means when we are increasing a voltage by 2 times, the current will also increase by 2 times. So nothing is gained over here, right? So therefore, under a sphere, you can see this figure. Okay. So under a sphere velocity saturations, the current becomes a linearly proportional to the input gate current, right? This is not desired, right? Therefore, we should not saturate our device in terms of velocity. Okay. This is the substrate current. This is not velocity current. So the heading is not correct over here. This is substrate current, right? And substrate current has this. This is because of the hot carrier basically, right? So here, this is because of hot carrier effect. When the hot carrier, when charge carrier achieves a very high velocity and it knocks down some of the bond between silicon and silicon around a drain, right? So it produces electron hole pair. So your out of these two, the one is attracted by the battery applied at the drain, right? For example, in case of an MOSFET, the battery applied at the drain is having a positive terminal, right? Therefore, out of these electron hole pair, the electron will be attracted by that battery, whereas this hole produces a substrate current, and that current is given by this, right? It is also exponentially dependent. So and this is a drain source series resistance, right? So this when the device becomes smaller, this series resistance of source and drain cannot be neglected, right? And it ultimately it has to be taken into care of, because it will otherwise reduce your delay, will degrade the propagation delay. This is the punch through, right? So punch through also comes into picture, because when your device dimensions are reduced, what will happen? Your the depletion width across source and drain will try to meet with each other, right? When they will meet with each other, their electric field will be pointing opposite to each other, and the magnitude of both the field is almost equal. So what will happen? Both are in opposite directions. Therefore, the total field effect will be zero. So when total field effect will be zero, there is a huge flow of electron from the source to drain, thereby giving rise to a very large current, and the output, right? So that large current basically produces very high heat, and that heat may burn the device. Okay. And then another effect is the output impedance with Vds variation. You can see that output impedance R naught is equal to 2L by 1 minus delta L by L1 by delta 1 by ID and all those things, right? So this here, if you see this curve, your basically output impedance should remain constant, but it is not constant, right? At lower value of VDS, it is dominated by channel length modulation, and at high value of VDS, it is dominated by impact ionization. Impact ionization try to reduce the output impedance, because impact ionization means production of a large number of electron hole pair. Electron hole pair are the charge, so that connectivity increases. So connectivity increases means the resistance will reduce, right? But in somewhere in the middle, channel length modulation tries to increase your output impedance, but DI will try to reduce the DI output impedance, right? So both are opposite to each other. So therefore, in this reason, your current remains almost constant. Okay. So these are the consequences of your short channel effects. That is, it gives rise to some currents, which may be a subthreshold leakage current, it is a gate leakage current, band-to-band tunneling leakage current, right? So therefore, there are the more other prospective devices which can be used for low power applications. SOI-based MOSFETs, FinFET, double gate MOSFET, tunnel FET, junctionless FET, and CNT FET. So in my view, nowadays the research is going on the tunnel FET and junctionless FET. Okay, and the CNT FET is the most probable solution in my view, because let's go to this is CNT FET, right? So in CNT FET we have to have a channel of the carbon nanotube, right? And this carbon nanotube as small as 2 nanometer can be grown, right? So 2 nanometer can be grown. It means that there may be a channel length of the order of 2 nanometer, right? So if it is of 2 nanometer, then the device will be highly fast device, and if it is so small, then it will also consume a very less power. But the problem associated as of now with the carbon nanotube FET is that you can see here the transition resistance between the channel and the source and drain region is the transition resistance between source and channel is about 3 kilo ohm, and so is there between drain and the channel, right? 3 kilo ohm is there. Therefore, total resistance becomes a 6 kilo ohm, and this 6 kilo ohm in this so small device, resistance is a huge resistance, and it will degrade the propagation delay of this device to a large extent. Okay. Therefore, as and when the technology is available with us to reduce this transition resistance between the channel and the source and drain, this carbon nanotube Mosfet will replace all of the Mosfets and will capture the market. So thank you so much for giving a patience hearing. So I can take some question and answer if it is there. Yes, please.
Thank you, sir. Participant, do you have any questions? Kindly ask. So if you are having any question, kindly ask. Okay, sir. I think no question is there. So thanks, Ashwani sir, for providing your valuable talk in the area of nano. Means the topic with the means how the material is going to be changed day by day, and how this material is used for in the modern devices for the IC application. So once again, thanks for accepting our invitation, sir, and delivering this wonderful talk for all of us. So thank you, sir.
Thank you, Ashish, for giving me opportunity. Thank you so much.
Thank you, sir. Thank you. Thank you.
And नमस्कार पंकज जी. पंकज जी
नमस्कार सर, कैसे हैं सर?
नमस्कार, और बढ़िया हैं?
हाँ जी बिल्कुल ठीक सर.
कैसी है गर्मी आपके चंडीगढ़ में?
कब आओगे सर इधर पटियाला, चंडीगढ़ और इधर अपना राजपुरा कब
लगेगा मिलेंगे आपसे.
अब तो सर एक सोच रहे हैं NIT जालंधर में एक सबको बुला लेते हैं सर, यहीं पर ही नोडल पॉइंट यहाँ पे बनाते हैं.
जी
सर कोई बुलाते हैं, आपको ही बुलाते हैं इधर ही.
बड़े दिन हो गए सर. नमस्कार जी सर.
नमस्कार.
He is Dr. Praveen Malik from Physics Department. Actually, electronics और physics, mathematics and humanities also. तो हम चारों ने मिलकर थोड़ा प्लान किया था कि एक्चुअली क्या है, मटेरियल्स पे सर का काम रहता है, डॉक्टर मलिक का मेरा डिवाइसेस पर है. तो हमने कि एक बार थोड़ा देखें सर, मटेरियल का एप्लीकेशन तो सारा बेस तो फिजिक्स ही है सर, इंजीनियरिंग का भी.
बहुत बढ़िया, सोशल इंजीनियरिंग होती रहनी चाहिए. सोशल इंजीनियरिंग चलती रहनी चाहिए.
अश्वनी सर मैं और मलिक साहब जो हैं, हम BSc के बाद से इकट्ठे हैं सर. आज तक हम 94 के बाद से इकट्ठे हैं. आई थिंक
हम भी आपके साथ इकट्ठे ही हैं.
जी सर
बिल्कुल.
चलिए सर, बड़ा अच्छा लगा आपने जो एक्सेप्ट किया हमारी रिक्वेस्ट. थैंक यू सर, थैंक यू वेरी मच.
चलो सर,
रियली वेरी नाइस टू सी यू सर. अश्वनी सर, थैंक यू सर.
थैंक यू.
चलो ओके सर, थैंक यू.
ओके, थैंक यू.
So, Dr. Pankaj, let us welcome at this STC course, and very good morning to you and all the participants who are joining this session. So, can we start, sir?
Yes sir, please sir. We can start now. जी.
तो नेक्स्ट स्पीकर आ गए अभी मलिक साहब.
हाँ, डॉक्टर रमन, he is with us. डॉक्टर रमन.
हाँ जी सर.
हाँ, he has joined.
Okay.
So let me introduce first Dr. Pankaj Kumar, the expert of this talk. Dr. Pankaj Kumar did his PhD in experimental condensed matter physics and has more than 15 years of experience in R&D as well as academics. At present, Dr. Kumar is a professor in physics and working as Dean of the PhD program in Chitkara University, Punjab. He has worked as a postdoctoral fellow at the Department of the Bioinformatics, Nanofusion Technology, CBNU, South Korea. His recent research activity mainly focus on LCD technology, self-assembled materials, surface morphology, nanomaterials and their application for the information display technology. He has published large number of the research papers in different SCI journals along with filed various patents. The part of his research work was presented in various international conferences such as the ACLC Japan, SID USA, IMID and KLCC South Korea, ECLC Slovenia, IMRE Singapore, NCLC Poland, ICLC USA and ICLC Japan again. He has received several best papers and outstanding presentation awards. Dr. Kumar was also awarded with the International Merck Grant Award 2011 in Germany for the best research of the year 2011 in the field of LCD technology. Currently, he is supervising large number of the PhD scholars along with he is the supervisor of the various postdoctorate students and he is the PI of the different projects like DST funding projects, like CSR funding projects in the area of the liquid crystals and nanophysics. Dr. Kumar is a reviewer of the large number of SCI journals. So it's my privilege to welcome Dr. Kumar once again at this 5-day program, and we are grateful to you that you have given this opportunity to listen you as well as the participants. So now I request Dr. Pankaj to present his talk. Over to Dr. Pankaj.
Thank you, sir. Thank you, Malik Saab. Thank you so much for giving me this opportunity to interact this wonderful audience at NIT Jalandhar. So thank you, sir. And I am just sharing my PPT within 1 minute, sir. Just.
लो बिल्स में कुछ ऑब्जेक्शन लग के आ गया मैं कह रहा था ना 8 तारीख के बिल होंगे उसको रुक जाएंगे एक बार अश्विनी को बुलाओगे
तो हम कॉल करके ही आ जाएंगे ठीक है थैंक यू सर थैंक यू सो मच
Malik Saab, I am just sharing my PPT. So,
okay sir, okay.
Are you able to see now?
Yes, it is visible.
Okay, okay. So once again, thank you, sir. Thank you, your team, sir. I am highly thankful to each and everyone for giving me this opportunity. So once again, thanks to all. Now you can see my this presentation is based on the vertical alignment of liquid crystal via self-assembled nanoparticles for display devices. As yesterday we have listened a very good talk from Professor, the first invited talk. And in that talk we have listened and we have gone through regarding the introduction part of the liquid crystals and then the theory behind the liquid crystals and their chemistry, their physics as well as application part. Here I am especially focusing on the vertical alignment of liquid crystals for the display devices. How we can use the nanoparticles to make the vertical alignment and how we can use that vertical alignment display device for the display device. So the outline of this presentation will be a little introduction about the liquid crystals, different LCD modes, because we are going to discuss here about the modes of the liquid crystal, that is the homogeneous mode, homogeneous alignment or vertical alignment or in plane switching or some other tilted switching. So basically we are going here to discuss the different vertical alignment modes. So different LCD modes. In plane switching mode is one of the important aspect of the liquid crystal display devices. Then we will come to the vertical alignment and there are different vertical alignment displays. We will discuss about those also. Techniques for the VA mode displays, whatever the researchers have been employed, and present approaches for VA LCD, that will be method for VLC using nanoparticles doping, and the second of way to achieve the vertical alignment is the VLC bi-capillary convected cell assembled nanoparticles on ITO substrate, and then we will summarize the presentations. So as you know, liquid crystal is a fascinating state of matter with soft crystalline nature, and soft crystalline nature with orientational order along with large optical anisotropy made pneumatic liquid crystal as a powerful component of electro-optical devices. As you know, liquid crystals has the positional order as well as the orientational order, and this orientational and positional order make them wonderful for the electro-optic devices. So orientational control is the important parameters for any display devices. The orientation of pneumatic molecules need to be controlled by electric field from external source to yield a specific orientation of the molecules without any external field. And an anisotropically modified surface is used. The most widely adopted method for controlling the direct orientation adjacent to solid surface is a coating of polymer layer on a substrate with transparent electrodes. So far, or I would like to say for commercial applications, the industries as well as the scientists, they are using the polymer layer for making the different LCD modes, means vertical alignment or some homogeneous alignment also. So they use the different polymer materials for homogeneous as well as the vertically aligned liquid crystals. So types of alignment of the materials, we talk about this, the for homogeneous, or we also call it planar alignment, in which liquid crystal director is parallel to the substrate plane. Polymer with short or no side chain is used. So substrate plane means the liquid crystal molecules will be the in plane of the surface. In case of the homotropic or vertical alignment, liquid crystal director is perpendicular to the substrate, and polymer with relatively longer side chain is generally used for make the vertical alignments. So vertical alignment was usually obtained for a liquid crystal with a negative dielectric anisotropy, while planar alignment was obtained with a positive anisotropy liquid crystals. So in general, when we prepare the LCD device, so vertical alignment, we usually use negative dielectric anisotropy materials, and for the planar alignment, we use the positive dielectric anisotropy materials. But there are some drawback of the alignment layer. The use of polymer layer has some drawbacks such as static charge and some debris due to mechanical rubbing and high curing temperature, as well as this method is not much applicable for the flexible displays, because in the baking, curing, rubbing, we have to bake this LCD substrate around at 200 degrees C. So that is not applicable in case of the flexible displays. So to liquid crystal alignments, if you see the planar alignment, vertical alignment or tilted alignments on this slide, in figure A, it shows the planar or homogeneous alignment, and is the director here, and you can see Z is the normal to the surface, as Z is has shown the normal to the surface, and theta is the angle between the normal of the surface and director of the LC. So in case of the homogeneous, you can see here the director is parallel to the liquid crystal molecules in both the figures. However, in case of the vertical alignment, the director is vertically aligned at the surface of the substrate. However, in case of the tilted, there is an angle between the director as well as the surface of the glass plates or substrates. So in vertically, I would like to say that liquid crystal molecules are perpendicular. In homogeneous, the liquid crystal molecules are aligned in parallel to the substrate. However, in case of the tilted, the liquid crystal molecules make some angle with the director of the liquid crystal molecules. These vertical alignments was first developed by Fujitsu in 1996. So the twisted pneumatic liquid crystal, which was one of the most widely used modes, and in that case, twisted pneumatic, if you see the old TVs at our homes, in your homes, or old even the laptop, etc., we use the twisted pneumatic display. So when no voltage is used to a twisted pneumatic liquid crystal cell or display, the light is polarized to pass through the cell. So in case of the twisted pneumatic, the light is passed when no voltage is applied, means at the zero voltage. However, when we applied the voltage, the liquid crystal cell twists up to 90 degrees, changing the polarization and blocking the light's path. By properly adjusting the level of the voltage, almost any gray level or transmission can be achieved. But in case of the twisted pneumatic, it results in blocking more transmission area, requiring a bright backlight, which consumes more power, making this type of display less desirable for notebook computers. So we need to move some other modes for improvement of these drawbacks of the twisted pneumatic display. So there are some conventional TFT LCDs. An advantage of conventional TFT LCDs are high resolution, lightweight, slim size, and low power consumption. But these conventional TFT LCDs also has some limitation, and the limitation is limited view angle performance, slow response time, and high manufacturing cost. So for mass production, these problems must be improved. So for improvement of these problems, different LCD modes are there. For high performance applications, on a number of new LCD modes in purpose to providing an improved performance are multi-domain twisted pneumatic mode, surface stabilized ferroelectric liquid crystal mode, anti-ferroelectric liquid crystal mode, and fourth one is optically compensated birefringence mode. However, most of these technologies not commercially successful. The commercially successful techniques are in plane switching and vertical alignment. At present, you can see at your home all the TVs and displays, mostly you will find IPS or vertical aligned. So vertical aligned is the most prominent display, I would like to say, because of some parameters. However, in plane switching are also in huge, and many of the TVs, many of the companies, they are using in plane switching also. IPS, however, IPS mode has a serious interesting problem in the transmittance. So that's why the vertical alignment based display are most preferred when we use at our homes or in offices, etc. So in plane switching, IPS was first suggested. In plane switching means IPS. So IPS was first suggested in 1992. It aligns the liquid crystal cells in a horizontal direction. Means the liquid crystal molecules are aligned in the horizontal direction at the substrate surface. In this, the electric field is applied through each end of the crystal, but this requires two transistors for each pixel instead of a single transistor, needed for a standard thin film transistor display. So the problem is it results in blocking more transmission area, requiring a brighter backlight which consume more power, making this type of display less desirable also for the notebook computers. So that's why the IPS as compared to the vertical alignment mode are not preferred. So scientists worked on the vertical alignment mode, and VA technology was first developed by Fujitsu in 1996. VA LCD's vertical aligned liquid crystal display provides an improved black level, high contrast and fast response relatively. In that case, in vertical alignment mode, the normalized transmittance can be described as T by T naught is equal to sine square to sine square pi d delta n effective by lambda. You can see here these equations where psi is the angle between one of the transmission axis of the cross polygers and the liquid crystal director. And effective is the voltage dependent effective birefringence of liquid crystal medium. जो liquid crystal के लोग हैं जो attend कर रहे हैं उनको I think they can understand it very well. So what is the meaning of this psi, what is the n effective, and what is this means lambda and T naught are in these equations. Anyway, the lambda and T naught are the wavelength and intensity of the incident light respectively. In absence of the electric field, psi is 0. In absence of an electric field, psi is 0, and the device appears black. T by T naught will be 0 when we put the psi 0. In the presence of the electric field, the effective retardation, that is D delta n effective, will start to occur, and we get the maximum transmittance when psi is the 45 degree. It means that when the angle between the psi angle between the transmission axis of the cross polyger and the liquid crystal director, means when aligned liquid crystal molecules are parallel one of the axis of the analyzer or polyger, then psi will be 0 and it will appear dark black. When there is a 45 degree angle between the liquid crystal molecules as well as one of the axes of the analyzer or polyger, then the maximum transmittance will be there. So in case of the vertical alignment, to get the maximum transmittance, we have to make the we have to make the arrangements in the way that the psi should be 0 when we want the perfectly black state, and psi should be 45 degree when we want the maximum transmittance. So different VA modes are there, because in simple VA mode, small view angles were its main disadvantage. Anyway, there was the high response, means very fast response, and the operating voltage is also less, but small view angle is its main disadvantage. So to solve this small view angle, the scientists solved by dividing each pixel into domains which work simultaneously, and this leads to the birth of different vertical alignment mode displays, such as multi-domain vertical alignment, and that was given by the physicists in 1998. The other mode of the vertical alignment display is known as the premium multi-domain vertical alignment, and that is given by the AU Optronics in 1999. After that, a super multi-domain vertical alignment was there, and it was given by the Optoelectronics and Fujitsu in 1999. After that, we can see here the pattern vertical alignment PVA mode, and that was given by Samsung and Sony in 2000. After that, the next advancement in vertical alignment mode displays was advanced multi-domain vertical alignment AMVA, and this is again given by the AU Optronics in 2005. However, again, I would like to share these all modes of displays requires much more complicated driving or pixel structure to realize the multi-domain. That's why these all techniques also are not commercially successful. So for a potential replacement of the rubbing methods as well as these highly sophisticated techniques, there are some other proposed techniques that is called the non-contact techniques, and these techniques include the oblique evaporation, photo alignment, Langmuir-Blodgett films, ion beam alignment method, and numerous inorganic materials such as diamond-like carbon, silica, silicon carbide, silicon nitride were studied with ion beam alignment techniques. It means that what I would like to convey here, these materials were coated on the ITO glass plate with the help of some different techniques. And scientists achieved a good uniformity in large size substrates, strong anchoring energy with high thermal stability as compared with photo alignment and oblique evaporation approaches. And after that, I would not I would like to share here the post material, means polyhedral oligomeric siloxanes. That was the silicon based. These materials, these nanoparticles were used in liquid crystals in 2007 for making the vertical alignment of liquid crystals. And I would like to tell or share that these materials, these vertical alignment of liquid crystal with the help of the nanoparticles was, I would like to say, was the first important note. I would not saying the revolution, but I would like to say this was the breakthrough. This paper was the breakthrough, and here we started to work on the vertical alignment of liquid crystal with the help of the nanoparticles. And not we, most of the groups, many of the groups, they are using the nanoparticles, and they started from this work only. So VA as well as in situ stabilization of the diopter tilt by bifunctional photoreactive self-absorbent monolayers has been achieved by the authors. Methods for the self-assembly of inorganic particles to yield two-dimensional monodomain crystal over a large area. And in that case, the people have used the different methods, that is the self-assembly under capillary forces, electrophoretic deposition, spin coating, spin casting, Langmuir-Blodgett deposition, as well as the convective assembly. So different authors, they have used the different methods to make the self-assembly of the nanoparticles for making the vertical alignment without any coating, without any sophisticated techniques. So present approach, in this present work, two different approaches have been used to get the vertical alignment of liquid crystals. First is the method for VLC using nanoparticles doping, And second is the VLC by convected self-assembled nanoparticles on ITO substrate. In the first case, what we have done, the nanoparticles were doped in the liquid crystal mixture. And in second case, the nanoparticles were deposited with the techniques that is known as the convective self-assembled on the ITO substrate. Both techniques use the very good vertical alignment on the liquid crystals, and I am very much sure that these techniques definitely will be more useful for the vertical alignment display devices, and companies will prefer these techniques to make the vertical alignment with the help of the nanoparticles. So consequently, multi-layered crystalline silica nanoparticles on the ITO glass substrates were deposited by evaporation-induced cell assembly technique and used for the VA for pneumatic LCs. Both monodisperse and polydisperse silica nanoparticles were used in the separate sets of experiments to create nanoparticles layer on the ITO glass substrates. Malik Saab, I would like to ask, everything is going okay? Because I'm...
Yes, sir, everything is fine.
Okay, ma'am. So I request to everyone, if they have any questions, any observation, please, they can discuss, and they can, anytime they can speak. Method for VLC using nanoparticles doping to the LC. Here, the materials and preparation of the cell, you can see here, negative dielectric anisotropy, as I told in general, for the negative dielectric and for the vertical alignment mode, the negative dielectric anisotropy pneumatic liquid cell is generally used. So here we use the MJ98468, which has the negative dielectric anisotropy delta epsilon is -4, and the birefringence value is 0.077. Isotopic temperature of this pneumatic liquid crystal was 75 degrees C. Spherical nanoparticles with concentration, types of shape and size, that is very important parameter when you use the nanoparticles. We cannot use the micro scale nanoparticles in case of the display devices, because they cannot give the desired characteristics as we want. So spherical nanoparticles with concentration 0.3 to 0.5 weight%. These 0.3 to 0.8% nanoparticles, these concentration is the most optimized value. Not only for silica, there are different materials, alumina, titanium oxide, zinc oxide, silica, etc. And different size of the nanoparticles have been used. You can see here 15 nanometer, 80 nanometer, 128 nanometer, and 320 nanometers. So when we were doing these experiments, as we are doing these experiments from last many years, so the size of the nanoparticles 15, 80, 128 and 320 are the most appropriate size. After that, we have used the 540 nanometer, 700 nanometer, 800 nanometer, 1000 nanometer, but these scale nanoparticles are not up to the mark when we talk about the display devices. So ITO glass substrates has been used. Cell gap according to the purpose. When we want to characterize voltage transmission characteristics, then we have to use the 4 micrometer. But when we want to calculate the anchoring energy, etc., then we can change the thickness of the display cell. So 4 micrometer and 10 micrometer we have used. Homogeneous dispersion of nanoparticles and pneumatic liquid crystal was prepared by mechanical string followed by ultrasonic process. And these methods, which we have used, prepared by mechanical string followed by ultrasonic process. So these mechanical string as well as the ultrasonic process, it needs proper care and proper handling. So mixture was loaded to cell at its isotopic temperature, either by capillary action or one drop method. In case of the LCD display, when we prepare the display cell, we can use both methods, that is called the capillary action as well as the one drop method. In companies, most of the companies are used one drop method also. So we have used both methods to make these methods applicable to industry also. So characterization, what we have done here, polarized optical microscope, conoscopy, electro-optic, or anchoring energy, etc. we have used. These are the most important parameters when we talk about the display devices. So POM and conoscopic images of nanoparticle doped LC. You can see here negative Lc plus 15 nanometer silica nanoparticles. Thus, figure B, you can see here at the 10x, liquid crystal plus 80 nanometer silica nanoparticles. And figure C, liquid crystal plus 320 nanometer silica nanoparticles. So these all size nanoparticles, 15, 80 and 320, they give very good dark state. Here it shows that these textures has taken under the cross pole, and in the cross pole, if the vertical alignment is there, then the initial state should be the dark state. You can see here very good dark state with 15 nanometers, 80 nanometers and 320 nanometers. Not only the silica nanoparticles, you can see here the figure D, E and F. Titanium oxide, aluminum oxide as well as the ZNO nanoparticles. All the nanoparticles when dispersed with the liquid crystals and prepare the display cell without any coating, without any baking, without any specific treatment, you can achieve the vertical alignment in the display cell. Here you can see here under the applied voltage at the 0 voltage it is perfectly dark, and at the 2 voltage you can see here there is something, the liquid crystal molecules start to change at the 2 volt, 2.2 volt, 2.3 volt, 2.4 volt and 3 volt. At 2.3 volt the perfectly bright state is there. So POM along with conoscopic image of the 15 nanometer particle size at 0.3% doped VSL with applied voltage 0 voltage, 2 volt, 2.2 up to 3 volt under cross polarizer, and the magnification was here 200x. So you can see here the perfect dark state as well as the perfect bright state. And I would like to compare these state with the commercially used polymer nanoparticle doped VSL also. So here you can see here the POM image of the 80 nanometers. So in case of the 80 nanometer, if you see the first slide, the previous slide here 2.0 volt. In the B figure here you can see here 1.9 volt, 2.0 volt and 2.0 volt. You can see here 2.2 volt, 3.0 volt. So 80 nanometer as well as the 15 nanometer, they are giving very good dark state as well as the very good bright state. And this figure is the image of the conventional PIVA cell under cross polarizer at a magnification of 200x. It means that polyimide vertical alignment layer was coated on the ITO glass substrate, and these polyimide layer in general used by the industry companies for the commercial application. But in figure 2.2, in figure 2.4, sorry, in figure C, in figure D, in figure E and in figure F, you can see here the images in the previous slides at 2 volt, 2.2 volt, 3.0 volt. It means that here the perfect bright state is there. It means that all the molecules are perfectly aligned in some particular direction. But here at the volt 2.4 volt, 3.4 volt, 4.0 volt, you can see there are it means that these figures, this texture shows that the liquid crystal molecules are not perfectly aligned unidirectionally. It means that they have some drawbacks inside the cells, and that's why we can see these kind of textures. We want, under the applied voltage, we want perfectly bright state for a perfect display device. So again, we are coming to the electro-optic and response time characteristics for these materials, these display cell. You can see in figure A, conventional PIVA cell, the black dotted graph can, with the help of the black dotted graph, you can see, and the red one is the 50 nanometer silica doped cell, and green one is the 80 nanometer silica doped cell. So threshold voltage, that is called the V10. We generally show it with the help V10. So V10 is 2.34 volt in case of the polyimide VSL. But when we are going to the 50 nanometer silicon nanoparticles as well as the 80 nanometer silicon nanoparticles, you can see here the threshold voltage is reduced from 2.3 volt to 2.15 and 1.95 volt. Similarly, you can see in figure B the response times. For the response time, when we use the PIVA cell, you can see here the response times is the 40.9 millisecond. But in case of the silicon nanoparticles as well as the different size of silicon nanoparticles, 50 nanometer, 80 nanometers, the response times are 34.5 or 34.75 millisecond. So it means that I am not saying that the silicon nanoparticle saving is the best one only and PIVA is not the good one. As you can see here, still the response time is still fast as compared to PIVA cell. So here 40.9 millisecond, but in case of the silicon nanoparticles, 34.5 millisecond. So it means that the silicon nanoparticles giving some particular angle, which is called the pre-tilt angle to the liquid crystal molecules. And liquid crystal molecules, if they have some pre-tilt angle and fixed pre-tilt angle, that's why the response time may be fast when we apply the field. So surface anchoring energy of conventional PIVA cells, voltage dependent RV plots of conventional PIVA cells, cell gap was here 10 micrometer and the anchoring energy was calculated by the equation. Here R by R naught minus 1, you can see here this equation K33 by WD into V minus V dash. So with these equations, we have, with the help of these equations and these parameters, we calculated the anchoring energy. And in case of the conventional PIVA cell means polyimide coated VSL, which is generally used by the companies. So the anchoring energy is nearly 2.047 10 to minus 5 joule per meter square. But in case of the surface anchoring energy of nanoparticle of VSL, you can see here the anchoring energy for 15 nanometer as well as the 80 nanometer. The anchoring energy is almost W is equal to 4.827 10 to minus 5 joule meter square. And 80 nanometer, this is 3.14 10 to minus 5 joule per meter square. So same order of surface anchoring energy of 10 micrometer Pi and SiO2 nanoparticle dispersible liquid crystals. It means that the anchoring energy is almost similar. The response time is fast. The operating voltage is very less as compared to PIVA cells. So these characteristics make nanoparticles dispersed display cells much more I would like to say applicable for the display devices as compared to commercially used polyimide or commercially used some other methods which are very sophisticated, which cannot be performed in each and every lab. Again, the second part of this presentations or this work is if we want to make the response time more fast as well as we want to reduce the threshold voltage or operating voltage, then pre-tilt control is one of the method. So in that case, pre-tilt control and in situ stabilization of liquid crystal by dispersed nanoparticles are also performed in the liquid crystal host. So in these experiments, again we have used the pneumatic liquid crystals of the same anisotropy as well as the same birefringence. The absolute temperature of pneumatic LC was same. Silicon nanoparticles, here we have used the 128 nanometer and concentration was we performed 0.3 to 0.58%. Substrates, that is very advanced substrate. Here we use the substrate fishbone pattern electrode glass, and fishbone pattern electrode glass is generally used for the wide view angle. So we changed this experiment with the help of the fishbone pattern electrodes. So we wanted to confirm that the every substrates are giving the vertical alignment or not. So cell gap accordingly 4 micrometer, 10 micrometer, and here to control the pre-tilt angle of the liquid crystals, we use the UV light of 100 microwatt per centimeter square at a specific wavelength 370 nanometer. So preparation of silicon nanoparticle of liquid crystal mixtures. The silicon nanoparticles were modified by photoreactive 3-trimethyl silyl propyl methacrylate. The surface modification accomplished through the silent coupling reaction by hydroxyl group on the surface of the silicon nanoparticles. And this was done with the help of some chemistry people. people. Homogeneous dispersion of surface modified silicon nanoparticles and NLC was prepared by mechanical string followed by ultrasonic process. So surface modified silicon nanoparticles was again used with the liquid crystal mixtures, and again it was mixed with the liquid crystal with mechanical string as well as the ultrasonic process. So mixture was loaded to the cell at its isotropic temperature, and we used here also the capillary action as well as the one drop method. So again we characterize this cell with the help of the POM conoscopy, electrophic and anchoring energy. So you can see here in this figure the planar anchoring when we before we are going to the vertical alignment of homotropic anchoring. Initially, the liquid crystal mixture as well as the nanoparticles, they are in the planar anchoring. They are in the planar state. You can see here this liquid crystal molecules are aligned parallel to the substrates, and these are the nanoparticles. So in homotropic anchoring, how these nanoparticles are going or are modifying the anchoring of the liquid crystal molecules, these nanoparticles are going to the surface. So 2D reference surface formed by randomly absorbed nanoparticles and consequent physical interaction with liquid crystal molecules, giving the vertical alignment of the liquid crystals. Then we have to control the pre-tilt angle. So here the liquid crystal molecules are vertically aligned. These are the negative dielectric anisotropy, and negative dielectric anisotropy liquid crystals has the property that if we apply the electric field, then they will switch in the perpendicular direction of the applied field. So here we applied some voltage on the cell, and then the liquid crystal cell was cured by the UV radiation. And in that case, if we are applying the 2 volts or 1.5 volts, then the 2.5 volts or 2 volts, they will, with the help of this applied voltage, the liquid crystal molecules, all the liquid crystal molecules, they will deflect in some particular direction. And at that time, we can cure these cells so that the pre-tilt angle can be maintained. So threshold voltage was applied to stabilize the pre-tilt of liquid crystal molecules under UV radiation. And here you can see the POM and conoscopic image before pre-tilt control at 0 volt, 2.4 volt, 2.6 volt, 2.8 volt, 3 point and 4.0 up to 4.0 volt. So POM along with conoscopic image, you can see here the conoscopic also, this one, of the surface modified silicon nanoparticle disperse vertical alignment at the fishbone, in the fishbone cell before polymerizations. Again, in the next slide, you can see here POM and conoscopic image after pre-tilt control. So after pre-tilt control, you can see the white state is much more better as compared to a previous slide. You can see here 3.6, 3.2, 3.0. So this indicates that the liquid crystal molecules are aligned in some particular directions. Electrophic and response time characteristics were performed in the fishbone cell also. And before curing, you can see here, this is very clear, 128 nanometer modified silicon nanoparticles were used. Before curing, you can see here the V10, that is the threshold voltage is 2.3 volt before curing. After curing means when we stabilize the liquid crystal molecules with the help of the UV curing, the pre-tilt angle was there, and the liquid crystal molecules can deflect, can switch with the help of the applied voltage at lower voltage. And you can see here with this experiment, the V10 after curing is 1.82 volt. V90 is 3.7 volt, and V90 after curing is 3.2 volt. It means that the operating voltage as well as the threshold voltage both are used when we are making the pre-tilt angle, when we are giving the pre-tilt angle to the liquid crystal molecules. Again, you can see here the response time also after curing, the response time, and before curing the response time. Here before curing the response time 75 millisecond, rise time, fall time is 51 and 23 millisecond. After curing the rise time is 43.5 millisecond, means response time. Rise time is 27 and fall time is 16. So voltage transmittance and dynamic response of modified silicon nanoparticle doped fishbone cell before and after polymerization indicates that if we control the pre-tilt angle, then we can reduce the operating voltage as well as the threshold voltage, and we can improve the response time. Improve means we can reduce the response time of the device. Again, surface anchoring energy was performed for this cell also. The same method we have used, and you can see here the anchoring energy is in the same order, and this anchoring energy is 3.14 into 10 to minus 5 joule per meter square. In next slide, after curing, the anchoring energy is 1.96 into 10 to minus 5 joule per meter square. So anchoring energy is also in the same order. So for any of the device, whatever we are using the ITO simple glass substrates, or we are using the some sophisticated substrates, in each cases we can get the vertical alignment with the help of the nanoparticles, and all the characteristics in terms of the threshold voltage, operating voltage, transmission, and dark state, as well as the contrast, all the parameters has improved a lot. How do nanoparticles induce vertical alignment in confined LC cell? Even at one slides, we have emphasized that the liquid crystal molecules and the nanoparticles in liquid crystal molecule nanoparticles are going to the surface, and they are modifying the surface, and with this modified surface the nanoparticles are going to vertical. So we localize for the confirmation of this experiment or our thought, we localize the silica nanoparticles on the substrate surface with a small quantity of reactive mesogen, that is Rn257 plus photoinitiator, and we exposed these with UV light at 100 micrometer per centimeter at a specific wavelength lambda 370 nanometer. Cell was dipped in hexane solvent over 2 nights by successfully reflexing. Only nanoparticles on the surface localized with the Rn. So I would like to say here, initially the silica nanoparticles were coated on mixed with the liquid crystals, and reactive mesogen was mixed. Then because reactive mesogen was there, so it was cured with the help of the UV light, with the irradiation of the UV light. So all the nanoparticles were deposited on the substrates. Then we reflex the cell, we dipped the cell in hexane to reflex the liquid crystal materials, and after that we can see the only nanoparticles on the surface localized with the Rn. Then again, I would like to confirm here, I would like to communicate here that the nanoparticles are going to the surface, and physical interaction between liquid crystal as well as the roughened surface are giving the vertical alignment of the liquid crystals. So this experiment was done with the for confirmation of are these nanoparticles are in the bulk liquid crystal materials, or these nanoparticles are going on the surface. So these nanoparticles, most of the nanoparticles are going on the surface, and they are modifying the surface. That's why they are giving the pure cell. Now VLC, the second approach which we have used, that is the VLC by convected cell assembled nanoparticles on ITO substrate. So in first approach we have used the doping of the nanoparticles. However, in this approach we have coated the nanoparticles on the substrate surface. So negative dielectric anisotropy nematic liquid crystal again we have used, and you can see here the dielectric anisotropy as well as the other characteristics. Here the concentration was used 0.05 to 0.28%. Here the concentration is less as compared to previous one. ITO glass substrate we have used, ball spacer and tape spacer both were used for the experimentation, and cell gap according to the purpose 4 micrometer as well as the 10 micrometer we have used. So preparation of thin layer of nanoparticle deposited on ITO glass substrates. Homogeneous dispersion of nanoparticles in deionized water, followed by stirring overnight and ultrasonic process at a frequency of 20 kHz for 24 hours at 60 degrees C using sonicator. Clean and dried ITO coated glass plates were dipped vertically in homogeneous dispersion of nanoparticles with different size separately. Samples were kept in a preheated chamber at 60 degrees C for slow evaporation of such solvent. and multi-layer cell assembly of nanoparticles was achieved on the ITO glass plates upon evaporation of the solvent. Mixture was loaded, mixture means the liquid crystal mixture, was loaded between nanoparticles coated ITO glass substrates by capillary action at its isotopic temperature. So what we have written here, it means that we just coated the nanoparticles on the ITO substrate, and for this coating the nanoparticles were mixed with the deionized water, and before coating the nanoparticles were well mixed with the help of some ultrasonic process as well as the stirring, etc. Then the samples were kept in pretreated chamber at 60 degrees C for slow evaporation of the solvents with the ITO coated glass plates. So after slow evaporation, the nanoparticles were deposited on the glass plates, and then the deposited glass plates were used for the liquid crystal display cell. And then liquid crystal materials were filled with the cell, which is made by the deposited nanoparticles coated glass plates. Again, the characterization was done with the help of the FESCM, AFM, POM, conoscopy, electro-optic and anchoric energy. FESCM, AFM and POM studies, you can see here figure A1, A2 and B and C and D. Periodic surface structure of the silica nanoparticles and electro-optic switching of the liquid crystal cell fabricated by the same. A to I. A first, normal. This is the normal view of the nanoparticle deposited on the glass plates. And second one is the A second. That is the tilted FESCM view of the surface of the nanoparticles. And you can see very beautiful picture of the nanoparticles. And the important things, you can see very homogeneous size of the nanoparticles here. These are monodispersed 320 nanometer silica nanoparticles. In the figure C, you can see the conoscopic image as well as the dark image at 0 voltage. This is the liquid crystal cell which is made by these glass plates, coated glass plates, and perfectly dark state you can see here. In figure D, you can see the white state. Although it is not the white state, but if we increase some voltage more, then it will go to the perfectly white state. So in figure B, you can see FM data exemplifying regular embossed surface with a hexagonal pattern. You can see here. In figure C and D, POM images of the cell at 0 voltage and 5 voltage, which I have discussed. The arrows denote the transmission axis of the polarizers. The inset in figure C is the corresponding conoscopic figures. So these all characteristics, these all FESCM, AFM data shows the very good coating of the nanoparticle on the substrate. And when we use these nanoparticles coated glass plates for the liquid crystal display cell, so perfect vertical as well as the perfect bright state achieved at the 0 voltage as well as the 5 volt. So again here you can see FESCM and POM studies, optical scanning electron micrograph and POM of the multi-layered nanoparticles with an average 15 nanometer diameter. In the previous slide here, the silica nanoparticle was of 320 nanometer size. Here the nanoparticles was 15 nanometer size. So I would like to say that the size from 15 nanometer to 300 nanometer, all the size are okay, and they can be used for the display purpose for making different alignment, means vertical alignment of liquid crystals. In figure A, optical image of the silica layer formed by varied deposition rate. In figure B, optical image of the thick deposition. FESCM visualization of the figure C, thin layer with normal view. And figure D, thick layer with a tilted view. You can see here the thickness of the layer also in tilted view. In figure E, magnified normal view of the thick layer. POM and conoscopic images of the liquid crystal cells fabricated with thin and thick silica layers, and it is given by figure F and figure G. So figure F, you can see here the perfectly dark state and conoscopy, very good conoscopic state. as well as in case of the figure C, you can see here the thick silica layers are there. Scale bars for optical image correspond to 10 micrometer. Here scale bars anyway, the bright lines in figure G, the important points here, the bright lines in figure G correspond to the cracked lines in figure B. In figure B, you can see the cracked lines and the corresponding, the bright lines in figure G can be seen. So POM images exhibits two distinct regions, a uniform thin layer upper part and a thick layer with many cracks due to volume shrinkage during drying. Lower part formed by fast and slow evaporation process. ये हम यहाँ की बात करेंगे. First figure A. In figure B, textures reveals evenly thick layer with many cleavages in a wide area, and in figure C presents a close packing of silica nanoparticles with no crystalline order, probably due to polydispersity of a particle size. And figure D shows the flat, smooth but thick deposition with a wide crack in slow process region. Figure F, this one is here, POM images. Figure F shows the layer, a thin layer produce the uniform vertical element as confirmed by conoscopy as well as the microscopy. And figure G, as I told at the earlier slide, represents thick deposition induced VA, although a random planar alignment was evidenced by the bright lines in cracked areas with bare ITO surface. So surface topography using AFM. Surface topography of the bare ITO substrate you can see here. In the figure B, the thick silica layer deposited using polydisperse 80 nanometers. So in that case, the nanoparticles were used at 80 nanometers. So you can see at the first figure, I saw the 320 nanometer. In the second case, I have shown the 15 nanometer, and again in these slides you can see here the 80 nanometers. So all the nanometer size from 15 to 500 nanometers, they are giving very good vertical alignment as well as the good characteristics in terms of the use of the nanoparticles for display devices. So the plots correspond to the surface profile along the green diagonals line in 2D images. The histogram exhibit the number of events counted by the height of discrete aggregates. So figure A and B shows the 2D and 3D views which presents irregularity of the surface, figure A and B. That is the bare ITO substrate as well as the silica coated substrates. The average and RMS roughness were 0.25 nanometer and 0.32 nanometer for bare ITO substrates and 22.4 and 28.9 nm for nanoparticle layer deposited ITO substrates. So you can see here the surface roughness is much more as compared to bare ITO substrate in case of the nanoparticle dispersed ITO substrates. The histogram in figure A and B shows the height distribution of protrusions, which shows 1.4 nanometer and 4.3 nanometer of average height of bare ITO substrate as well as the nanoparticle layer deposited ITO substrates. As there are the multi-layer of the nanoparticles, so this height distribution can be 1.4 nanometer in case of the ITO substrate. However, in case of the silica nanoparticles, due to multi-layer, it is to 14.3 nanometer, which shows that the multi-layer depositions. The surface roughness of the nanoparticle layer is approximately 2 orders of magnitude larger than that of the bare ITO substrates. So electro-optic characteristics for this device also. You can see here the threshold field 22 volt in case of the nanoparticles and PI cells, 2.0 volt for the nanoparticles and 2.4 for the PI cells. Saturation voltage, that is 4.0 volt in case of the nanoparticle deposition and 3.9 volt in case of the PI cells. So saturation voltage almost similar. The turn-off time 2.2 millisecond in case of the nanoparticle deposit. However, in case of the PI cells, it is 13.0. The turn-on time 11.5 millisecond and 27.9 millisecond in case of the PI cell. So it means that the response time is faster in case of the nanoparticle deposited device as compared to PI cell. So electro-optic switching characteristic of LC cell with cell assembled 15 nanometer, you can see here in this figure. The inset presents POM images of the dark and bright state for the nanoparticle cell at corresponding applied voltage, 5 volt as well as the 0 voltage. Surface anchoring energy in this case also has been measured, and we use the same method, that is the RV method. And anchoring energy was calculated with the help of this equation you can see here. The anchoring energy for 15 nanometer nanoparticle size 5.51 into 10 to minus 5 joule per meter square. However, in case of the conventional PI, the anchoring energy was 2.11 into 10 to minus 5 joule per meter square. So again, the anchoring energy are in the same order for 15 nanoparticles deposited cells as compared to a PI cell. So if I summarized this work, the advancement in novel VA technology, the spontaneous vertical alignment obtained by the absorption silicon nanoparticles at the inner surface of substrates in both methods with improved electro-optic characteristics, the stabilization of the direct tilt by the polymerization of modified surface of silicon nanoparticles under the predetermined multi-domain director tilt facilitated by the fishbone pattern electrode and applied electric field. Polar anchoring energy is also of the same order of conventional devices. Thus, silicon nanoparticles VLC has splendid potential application to produce high informative VA mode LCDs with an easy manufacturing process. So I would like to acknowledge Professor K.K. Rana, who is my supervisor, also PhD supervisor, and at present Vice Chancellor of Ramaiah University Applied Sciences, Bangalore. Dr. Parveen Malik, who is my fast friend and is working at NIT Jalandhar. Professor S.H. Lee at Chonbuk National University, South Korea. Still we are working together, and some of the part of this work has been done at the University of Chonbuk. Professor Sinwoo Kang, he is also from South Korea. Dr. Vandana Sharma, she is my PhD scholar and now assistant professor at Chitkara University. Mr. Ankit Rai Dogra, he has done the last work. He is PhD scholar and SRF in DST SURF project. So finally, I would like to acknowledge the SURF DST for financial support as well as the DST Inspire, which has given the fellowship to Dr. Vandana. So thank you for everyone. Thank you for giving me this opportunity. Thank you, sir. Thank you so much. Any questions or any suggestions, I would like to receive. Thank you so much.
Thank you, Dr. Pankaj. Now we can take one or two questions. I'm audible?
Ji sir, please. Ji. Any suggestion, not only question, any suggestion on the presentation, any suggestion on the work and what we can improve more? Please, Sonali MK has raised his hand.
Yes.
Sonali, please.
Sir, am I audible?
Ji, please.
Sir, thank you for a very informative talk, because I am just stepping into a similar kind of a domain in the field of liquid crystals. Sir, and it helped us a lot, and we are also doping it with zinc oxide. But the domain in the liquid crystals which we are working are smectics mostly. So
Okay,
so what is your opinion on the smectic kind of an alignment? Like where can we apply it? So this was totally on pneumatics, right? So
Yes.
how like, what do you say? Do you prefer pneumatic and smectic? How can we go about the alignment in smectics is something which I wanted to know from your side.
Okay.
Yeah.
Yes, ma'am. These all work has been done with the pneumatic liquid crystal system, but now we have initiated in the semitic or ferrotic liquid crystal also. I am very much sure if we use the semitic system, then definitely we can modify the anchoring condition of the liquid crystal molecule with the help of the liquid crystal, with the help of the nanoparticle dispersion or deposition of the nanoparticles.
Yes, sir. Actually, we are synthesizing it, and we are yet to do the electro-optic studies. So this talk of yours helped us a lot to give an idea on how to proceed our work. Thank you.
Definitely,
so
ma'am.
much.
Definitely it will help, and you can later also, if you have any point to discuss, then anytime you can discuss, you can mail or you can call.
Yeah, sure, sir. Thank you. I would need that. Yeah.
Thank you.
sir.
Thank you.
Thank you.
Thank you, Sonali ma'am.
Dr. Pankaj, we have another question from Omkar Das.
Ji, please.
Question is, which device is used to measure birefringence of a LC material?
Okay, birefringence. Actually, generally we are not measuring the birefringence because birefringence already they have given most of the materials. But if we want to use the birefringence, then I think Malik Saab, you also know we can use the optical microscope also for the birefringence.
Yes, sir. We can calculate the transmission through the cell.
Transmission,
Okay.
we can calculate transmission and then we can calculate the birefringence.
And by using some relationship, we can calculate the birefringence delta time.
Yes, sir.
Dr. Saab, we have one more question. That is by Gaganpreet. Gaganpreet, are you there?
Gaganpreet, are you there?
Yes, sir. Good morning, sir.
Ji, good morning, Gaganpreet. Ji, please.
So my question is, why can't we achieve the vertical alignment using positive anisotropic materials? So as you
Yes,
said,
yes.
yeah, we can achieve only with negative anisotropic
No.
material.
I told that in general we use the negative dielectric anisotropy material. But when we use the IPS cell, then we cannot use the negative dielectric anisotropy liquid crystal. Then we have to use the positive LC. Okay. So we can use the positive LC also, but in that case, the anchoring condition, initial anchoring condition will be different. If initially you are using the IPS cell in which the liquid crystal molecules switch in the plane only, so then in that case you can use the positive LC.
Okay, sir. Okay, fine.
Dr. Pankaj, one more question. We can take only, due to shortage of time, we will take only one or two questions.
Ji, please.
Dr. Anuja Jain,
Yes, sir.
she's asking, so
Good
what is the
afternoon.
source? Good afternoon, Anuja.
Yes, sir. I have 2-3 questions, but I will try to finish it quickly.
Go ahead, please.
Ji, Anuja, please.
First question is from where we can procure polyamide.
Source of power.
Okay.
It's I am trying hard. But I
Ji.
couldn't.
Very difficult to collect the polyamide, and I collected it from Korea only.
Okay.
My students and myself also, we have gone through many of the companies, but still we couldn't find right one
Yes.
from where we can collect it. So it is the big question. Yes.
Dr. Anuja,
Yes.
that is available, but not in India. Okay,
Yes,
one of my known friend has procured some time back. Okay. So you can just send an email to me. I will forward you the address of that.
Oh, sir. Thank you, sir. Thank you so much. Sir, another question is, do you use any software for calculation of anchoring energy?
No, ma'am. We are not using any software. We are using, that is the RV technique, retardation and voltage method. So we have to calculate the retardation for that.
Okay, RV technique. Okay, sir.
Ji.
And another one is, can we use SNP, silicon nanoparticle deposition for the fabrication of polymer stabilized liquid crystal cells,
Polymer
PSLC?
stabilized liquid crystal. Definitely, Ji. You can use.
Okay, sir. For that, I will contact you through email for the guidance of SNP technique.
Ji, definitely, Anuja. You can see one paper in PDLC, polymer dispersible liquid crystal, that is the reverse mode PDLC.
Yes, sir.
The work has been done by Dr. Vandana Sharma.
Okay, sir.
जी, तो आप देख सकते हैं 2-3 पेपर हैं उनके, तो उसमें उन्होंने वर्टिकल अलाइनमेंट, उन्होंने पीडीएलसी में ही वर्टिकल अलाइनमेंट बनाया है जी.
ओके सर. वैसे मैं आपका वर्क प्रेफर करती हूँ. यस सर.
जी.
मालिक सर का आपका.
Dr. Anuja, you are working with Professor Deshmukh ji?
Yes, sir. I am working as a woman scientist there.
Okay, very good. Congrats.
Okay.
Please convey my regard to sir.
Thank you, sir. Yes, sir. Sure, sir.
Thank you.
And Dr. Manoj Malik is also there.
No, sir. No, sir. Yes, sir. He was my senior, but now he's working in Delhi in some college.
Okay.
Yes, sir.
जी, it's a long time to talk with Deshmukh sir and Manoj ji, but they are very well known to us. Dr. Malik.
Yes, sir. Yes, sir. We know it. Yes, Manoj is also came there earlier to learn some work from you.
जी.
Yes, sir.
Okay, so participants, if you have some more question, you can ask. Otherwise, I have to convey my thanks to Dr. Pankaj. Okay, if no other questions, so let us thanks once again. And Dr. Pankaj, thank you very much for sparing your valuable time. And I'm sure your talk, particularly on vertical alignment technique for the liquid crystal system, will be highly beneficial to those persons who are trying to learn new techniques for the display applications. So once again, thank you very much.
Thank you, sir. Thank you, Malik sir, and thank you for whole team. You all has provided me this opportunity, and I am very thankful to everyone, NIT Jalandhar and your director, sir, everyone. Thank you so much, sir.
Thank you, sir.
Thank you, audience. Thank you so much.
Participants, we have just shared the feedback performer in the Google form. You just fill it and submit the feedback.
So once again, thank you everyone. Thank you, sir. So can I leave, sir?
Yes, sure.
Okay, sir. Thank you, Ji. Thank you. जितेंद्र कुमार कुशवाहा, सर प्लीज, कैसे हैं सर? हाउ आर यू सर? They have raised hand. He has raised hand. Jitendra sir, you want to say anything? आपकी आवाज नहीं आ रही सर हमें. कुशवाहा सर, आपकी आवाज नहीं आ रही है जी. कैन यू हियर अस? Kushwaha sir, I am still waiting for you, but we are not able to hear you. Anyway, sir. ठीक है sir, I will call you sir and we will talk on phone because your voice is not coming to us. Maybe some technical problem is there. ठीक है sir. Okay जी, okay sir, thank you जी.